So works. So hi everybody, welcome back to another seminar of VTSS. Special thanks to Zhongjun and Alfred for joining us for our presentation and discussion. Today we're going to hear about the optimal transportation approach. The rules of the game are the usual. We go for around an hour. If you have any clarification questions in the middle, feel free to unmute and just ask me questions. Then we turn the recording off and we open up for question and answers. And I would say let's get started. And Zhongjun, we're looking forward to your presentation. Thanks for being with us today.
Thank you for the introduction. Also, I want to thank everyone for coming to the talk at a very busy time of the year. So this paper is joined with my colleague at BU, Zhongjun. And he knows 10 times on the topic than I do. This is my actually first adventure into optimal transport. I look forward to learning more about this topic. Also, this means I'm a little bit nervous about it. So fingers crossed. By the way, we plan to put the paper online after this talk. So I really look forward to your comments and suggestions. Let me begin with a one-page summary of the paper. We're interested in dynamic models that are potentially misspecified. Today, I will try to present results on 3 such models. The first model is going to be a simple trend cycle decomposition. The second model is a medium-scale DST model with a high-dimensional state vector. And the third model is a term structure model for interest rates. Models like this often involves policy-relevant latent variables. For example, we might have a cycle component of GDP in a trend cycle decomposition. We have productivity shock or other shocks in a DST model, or we might have asset pricing factors in term structure models. Because those models are not directly, these variables are not directly observed, they must be recovered from the data using some filtering techniques. That might include Kalman filter for linear setting or particle filter for nonlinear models. Our algorithm is going to cover both cases, linear and nonlinear. However, at the same time, the results for estimation, inference, and testing are for the linear case only. So the starting point of this paper is a very simple observation, which is that when dynamics are misspecified, filter updates are biased. This has 2 consequences. The first is that the filtered variables that we extract using particle filter or Kalman filter may not satisfy model restrictions. Another consequence is that the parameter estimates actually may fail to character model dynamics. I realize that the meaning of these 2 sentences might not be quite clear, but I'll have a couple slides to further illustrate these points. So our approach to address this bias issue is to use optimal transport. So what we do is kind of try to build a coupling between data and model in a dynamic way so that the filtered variables will be model consistent by construction. So as you will see, this approach also leads to methods for estimation and procedures for testing, and they all can be done in a unified framework. So just to summarize a little bit, this paper is about filtering, is also about estimation and model misspecification analysis. So that's a very quick preview. My plan for the talk is the following. So I'll begin with kind of illustration of the bias problem using the simple trend cycle decomposition. After that, I will be able to present optimal transport filter, which we introduce. We present, we kind of, this is the first result of the paper. So I will introduce this in a more general setting. This setting can be linear, can be nonlinear. It doesn't really matter. Then I will insert a slide about the related literature. After that, I'll be presenting a fast algorithm for linear models. And for this part, I will be showing you guys closed form expressions. If you look at the first 4 bullet points, they are mostly about filtering given parameter values. In other words, they do not really address the issue of parameter estimation. And this issue is addressing bullet point number 5. There we'll have methods for estimation. We'll also have large sample properties for that. Then I plan to conclude the talk with 2 additional empirical applications of some aspects of those applications. And the first is to a medium scale DSG model. The second is to a R5 term structure model. So in addition to these, I also have a few technical slides on derivations and asymptotic analysis. I'll be happy to show share them with you guys if there's time. Okay, so here we have a very simple model for trend cycle decomposition. The model is taken from Watson 1986 without any modification. In this case, we have a YT variable, which is a scalar random variable that corresponds to log GDP. And the model assumes that this variable has 2 components. And the first is a Gaussian random walk component, is a trend component. And the second component is a cycle component that follows a stationary AR2. The shocks to the 2 components are required to be RID, independent of each other for identification purposes. Here, the sample contains quarterly observations from 1947 to 2023, which includes the COVID period. By the way, for the meta notation, the delta here indicates actual observations. When there's no delta, it means the variable is taken from the model. It's not actual observation. And this difference is important when there's a misspecification because these 2 sets of variables are going to follow different dynamics. The model has 2 latent variables that need to be recovered using filtering. And the first is a trend, the second is a cycle. Here, the focus is going to be on the cycle component. Because the model is, of course, linear and errors are normally distributed, we can just apply a standard Kalman filter and then estimate the parameters using maximum likelihood. If we do this, then we get the figure on this slide. So the x-axis corresponds to time. The y-axis is the magnitude of the cycle component. The horizontal line is the 0 line. Of course, this estimate of the cycle component does not make any sense because it tells us that we were kind of in a permanent expansion starting from 1960 that goes all the way to 2010. Right, so it's really hard to interpret. It's really hard to believe that this is the actual cycle component. The explanation for this is, I guess, somewhat clear. It has been documented. Is because that the Gaussian random walk is a poor approximation to the trend component. As a result, the Kalman filter attributes most of the variation in the data to the cycle component, which is more flexibly specified than the trend component. So there's cross-contamination going on during the filtering process. In addition to that, the filter cycle does not seem to have a mean of 0, which contradicts the model restriction. If we go back, you see that this cycle component is meant to have mean zero, and the actual estimate is mostly positive. So we have some sort of model inconsistency showing up in this figure. Next, I'm going to quickly show you guys what we get if we apply the OT filter that we propose in this paper. And you will see that whenever we apply such a filter in our setting, it's going to involve two models, not one. One model, of course, is the model that we want to estimate, is this trend cycle decomposition model. And there's going to be a second model that provides the components that we need for transportation. In this case, the model is specified as on this slide. YT contains intercept, linear trend, and the sum of two cosine components. The cosine components are intended to capture the smooth variation in the trend. Here we have 4 terms such that the shortest periodicity is about 20 years, so that we don't confuse the trend with the cycle. At the same time, the residual component UT is assumed to be stationary to follow AR4 representation. We actually have varied the lags between 2 and 4. The results are not sensitive to this choice. Now we have both models, a reduced form representation and a strata model. We can build a coupling between the two, and the details will come later. I just want to show you guys what we get if we apply this approach, and this is the trend component that follows from that. And this is clearly, at least to us, much easier to interpret. For example, if you look at sharp declines in the component, they tend to align very well with NBR recession periods. In particular, we see the more recent COVID pandemic. We see the 2008, 2009 Great Recession. We also see the 1980 deep recession. So we do get a sense that we are looking at a cycle component, which is quite different from what we got from Kalman filter. I think the intuition for this is that now the model is still misspecified, but the misspecification is localized to the trend component, and the cycle is not getting contaminated, so we get some results that are much easier to interpret. Additionally, when we implemented this, we didn't make any adjustment for the COVID period, so the result is kind of a nice surprise that we didn't actually need any adjustment for that. Skip this. So now we have kind of a toy model in the background. This slide shows that the problem can be actually demonstrated in a very general setting. So here we have a general state space model. It can be nonlinear, can be linear, it doesn't really matter. So here I'm breaking down the filtering process step by step so that we can trace the problem to the very, we can get to the very bottom of the problem. So here, what I have is that we have some sort of initial belief about the latent state vector z t minus 1. In particular, t can be the initial period, so that we have initial belief about things at time 0. And in the next period, model will generate a prediction for y1, z1, or yt, and zt. And after that, observation arrives to the scene, and the model updates the belief, taking account of this new observation using BS updating. Then it gets into another round of prediction, observation, updating, and the process continues, and so forth. If the model is well specified, the entire thing is internally consistent, everything works. However, when there's misspecification, some strange things will happen. So here, misspecification means that the actual data dynamics, this with tildes, are different from the dynamics implied by the model. There's a second P that does not have a tilde. So we have kind of two sets of dynamics that are incompatible with each other. Here we can start with the same belief at t-1. The model generates a prediction. At this point, everything works, nothing's wrong. But then we observe instead yt, we observe yt tilde. So keep in mind that yt tilde and yt follow different dynamics. And in the next step, we try to update our belief about the state vector. We get some sort of a mismatch, right? Here, mismatch happens because yt does not follow pt, it follows pt tilde. So in a sense, yt tilde and pt are not compatible with each other. Because of this mismatch, the BS updating is biased, so our belief will be biased as a result of that. In step 4, when we carry out a prediction for the next period, because a prediction is based on a biased belief about ZT, the prediction is also biased. And as a result, when we continue this process, the bias will propagate and may even accumulate in the system. As a result, the filtered states, ZT, become very hard to interpret. So that's kind of an illustration of the problem in a general setting. It also kind of tells us what can be a solution to the problem. Because the problem is caused by a mismatch, so that we see if we can somehow get rid of this mismatch, we will be able to generate filtered state variables that are model consistent. Our approach is to borrow from the optimal transport literature that will allow us to add a step between step 2 and 3, so that the mismatch problem will be eliminated. I'll present you guys the details in a few slides. But then we can take a closer look at the consequences from this model inconsistency. I think I already said at the beginning that a result of this is that the filtered values or filtered variables may not satisfy model restrictions. In the trend cycle decomposition example, we saw that the sample average of the filtered series can be substantially non-zero, even though model assumes that this process has been zero. So we get one sort of model inconsistency there. In another setting, in this case, maybe we are looking at the DSG model, we can get filtered shocks that are cross-correlated, even though they are supposed to be independent from each other by assumptions. We can get another sort of model inconsistency due to this misspecification. A second consequence, which I think is equally important and is not as often documented in the literature, is that the resulting MOE may actually fail to characterize the dynamics of the filtered variables. And this can be illustrated using this table, which I took from the DSG application that we include in the paper. The details are not very important, but the key issue is that if you look at the Smith-Waters model, the model has 7 shocks. The first 5 of them are AR1 shocks. The remaining 2 of them are AMA11 shocks. So they are all serially correlated in some way. In the table, I have 7 columns corresponding to the 7 shocks. I have 3 rows that correspond to different different estimates, I would say. The first row gives the 2 serial correlation, in this case, first order correlation of those shocks, they are computed directly from the model. For example, in the case of investment, I look at the estimated, the MOE, right? The estimated AR1 coefficient is 0.47. So I know right away, the model is telling me that the correlation should be 0.47. The second row gives us the empirical first order correlation from the Kalman filter. So here, if you look at the investment shock, the empirical correlation actually is 0.83. This is much higher than what the parameter estimate is telling me. Similar features can happen to other shocks. For example, if we look at monetary policy shock, the model is telling me that the first order correlation is 0.47. But if I look at actual filtered shock, the correlation is pretty much equal to 0, right? For the price markup shock, the model is telling me that the correlation is 0.42. The actual estimate is almost equal to 0 again, which is quite different from the true value. So if our focus is to attach some interpretations to the estimated shocks, here we kind of run into difficulties, right? Because what the model is telling me is different from what I'm getting from applying Kalman filter. And the issue reflects the inconsistency that we see in the previous slide, because the specification error accumulates over time. Things are kind of hard to interpret as a result. So in the third row, I have pretty much the same thing, except that the correlations are computed using filtered values from the OT filter. There, if you compare the first row with the third row, you see that their values are much closer to each other. So we do get a sense of model consistency in this comparison. Okay. So now let's, do I need to pause for questions or should I keep going? Okay, I'll keep going. So now we will go back to this general setting. I will show you guys how we can address this issue using optimal transport. So the idea is that we're going to insert a step between step 2 and 3 so that there's no longer any mismatch and the belief updating will be internally consistent. For that, we'll have, of course, 2 models going on still, as in the trend cycle decomposition. The data correspond to the blue component. We have a distribution that's provided by a reduced form auxiliary model. The model is in red. We get a conditional distribution implied by the structural model or the state space model that we are looking at. So here we'll borrow something from the optimal transport literature. We try to build coupling between these 2 marginal distributions so that the joint distribution will respect both components. And from that, we can transport the actual observation, which is YT tilde, to the model to get a model consistent value, which is YT. I'm sorry here, I do not have closed form expressions because this is for the general setting where things need to be done numerically. But once we look at linear models, I will have closed form expressions that shows you guys precisely how the observations get transported to the model to get YT. So here, since we get YT, instead of YT tilde, subsequently, all the updating will be based on this new YT instead of YT tilde. This, by construction, eliminates any model inconsistency that showed up in the gamma filter or particle filter that we looked at. So here, I guess our contribution to the literature is that we embed this optimal transport step in a dynamic setting, and we show that we can actually get model consistency easily as a result of that. So this picture kind of is a further illustration about what goes on in this process. Here, OT stands for the transportation step. If you look at the bottom of this figure, we have updating that's based on the transported values instead of the original observations. I guess it's also kind of important to emphasize that here the transportation is done iteratively over time. It cannot be done in one step because the current transportation depend on the previous steps from the transportation and from the updating operations. So it's kind of alternation between filtering and optimal transport. So that's for the general case. As kind of, I hope it's already clear that it can be done in principle for nonlinear models. But at the same time, because there's a numerical component to it, it's going to be computationally intensive, and it also has cursive dimensionality going on in the process. For the remaining of the talk, I'm going to focus on linear processes. For that, we'll see very tractable expressions, pretty much closed form. We get semi-parametric algorithm that's fast to implement that does not suffer from the cursive dimensionality. Okay. So it might be a good time to relate to what we do to the broad literature on optimal transport, I guess. First of all, there is exciting and expanding literature on optimal transport. Here we have a very nice book about optimal transport and economics, which one can enjoy reading on the weekend. The work is also kind of related to the literature on simulated method moments or indirect inference, in the sense that we also look at auxiliary model, but the focus, I guess I can say, is very different. Then we also can kind of appreciate that what we do is related to this literature on minimum visiting distance estimation. To the best of my knowledge, most of the studies in this feature are for static models. Papers on dynamic models are extremely sparse. Actually, the only paper that I am aware of is on finite state markup chains. So we hope that what we do here can add a little bit to this dynamic aspects. Dynamic part of this literature. Since we look at structural models that are potentially misspecified, the work is kind of related to this DSG literature that look at misspecified DSG models. But again, I can say that the focus is quite different. We are not trying to fix the model. Instead, we want to get filtered estimates that are model consistent. We want to get estimates of the prompt values that are easily interpretable. Okay, so now I want to be more specific about the linear models that our framework can analyze. So in this case, the state space model is going to look like the system that we have on this slide. We have two blocks of equations. The first block corresponds to a measurement equation. In this case, yt is typically a random vector, and zt corresponds to the latent states, and zt is a vector that can be high dimensional. For example, if we look at DSG models, zt can have 30 or 40 components in it, and that's not a problem for algorithm is not a problem for estimation either. I also want to emphasize that even though VT are assumed to be serially uncorrelated, we don't have to impose restrictions on its distribution. In particular, it does not need to be normally distributed. The reason for that is that, as we'll see in the next couple of slides, the transportation involves only the first two moments. The higher order moments do not interfere with this process. For the auxiliary model, we'll be working with VR of order k. Here is intended to be an approximation to an infinite order vector autoregression. So in that sense, we are looking at a semi-parametric approximation. I mean, semi-parametric setting where we are using VR as a sieve approximation to a more general data generating process. As in the state space model, here the errors are white noise, and we do not impose distributional assumptions on this error term either. Okay, so the two models are in place. We can look at some closed form expressions as a result. So here we have two blocks going on. The first block is provided by the auxiliary model, which is the VRK. For each time period, we'll get a conditional mean of YT tilde, which corresponds to mu t given t minus 1 tilde. We also get a conditional variance of the same quantity. In this case, is given by sigma tilde. So when we specify the VR model, when we estimate its coefficients, these two components are very easy to get because they are just the first moment and the second moment. The second block comes from the model. Here we have this red block. So the conditional means given by mu t given t minus 1. And when we run the gamma filter, this is a direct outcome from that. The variance is sigma is also a direct consequence of the filtering process. I guess the bottom line is that those components that are needed for transport are quite easy to get. They are kind of closed form, and they do not involve any numerical aspects. They do not require simulations either. In this case, the linear transport map is linear. So the outcome from the transport YT is the sum of two components. First component is is mu t given t minus 1 that comes directly from the model. That's the prediction generated by the model. The p component is crucial for this transport. It depends on the variances from the auxiliary model and the variances from the structural model. And we also have a close expression for that. As a result, no simulation is needed. The ET component comes directly from the reduced form model, the VRK. In this case, is simply the residual from that approximation. I have a few slides that shows how this map can be derived as a consequence. I can share with you guys if there's time. Otherwise, these expressions are included in the paper. So actually, everything that's in the slide is already included in the paper for quick reference. Okay, so now we have a map that's linear, kind of in closed form. We can embed this map in the original filtering process. We get something like this. So the prediction step is the same as in a standard gamma filter. No modification is needed. The transport step is the same as what I've presented in the previous slide. We have closed form expressions, relatively easy to compute. The updating step is also essentially the same as that from the Kalman filter, except that we have this P matrix showing up. We also have this residual from the reduced form regression showing up. And this difference accounts for the mismatch. As a result, all the updating is internally consistent. So in a way, we can think of this optimal transport filter as an adjustment to the standard Kalman filter, in which this P matrix brings in a component that accounts for the mismatch between the data and the model, such that we can recover model consistency. If it turns out the model is well specified, so that there's no misspecification, the P matrix will reduce to an identity matrix asymptotically. As a result, we are back to the standard Kalman filter. And this means that the filter includes well-specified models as a special case. So we kind of have a continuous connection between well-specified models and misspecified models. In both cases, we will have filtered estimates that are model consistent. Okay, so that's the OTF filter that we implement for linear models.
Ready?
Yeah.
Oui. I have a question, sorry. If I understand right, you have a model which is misspecified, which is a linear model, and I mean with a latent variable, and then there is an approximation of a true model. Your VAR is like an approximation of a DGP, right?
Yes.
But if this approximation is a good approximation of a DGP, you could work directly with this model, right? So, what does it bring you to use the other model?
Yeah. Thanks for the question. That's a great point. So, if the goal is to get predictions, then this analysis is not relevant. So our goal is to estimate the structural model, to get estimates of the structural coefficients, and try to generate filtered state variables. So this structural model could be a DSG model. It could be as a pricing model. So that's going to be the target of the analysis. So the goal is not forecasting, but instead is to carry out some sort of structural analysis.
Okay, so it's estimating actually the wrong model. It's very, yeah.
Yeah, so so our starting point is that we have a structural model. It might be potentially misspecified. It might be well specified. We do not know. We would like to have a procedure that's robust in some way, so that our filtered states will be easier to interpret, or be more consistent. So we are aiming for that target.
Okay, thank you.
Okay. So that's
tell me if I'm wrong. So this means the researcher needs to know that the model that he's working on is misspecified, and he needs enough information of the true model to do this correction step. Am I correct?
You are.
I mean, I'm not into this literature model misspecification. This might be standard, but just to check I'm on the right page.
Yeah, so I think you're right. So the structural model could be misspecified, could be well specified. Both are fine. But at the same time, the VR model is expected to be well specified as approximation to the underlying data generating process.
Okay, so that's an underlying assumption.
Yeah, that is.
Because you mentioned robust, so this is not robust across the true unknown, not misspecified. It is not a robust in the sense of the robust literature, right?
So here, this VR model is used as approximation to get the first and the second moments of the underlying data generating process. As long as we are comfortable with this aspect, I think we are fine. At the same time, if we believe that VR is not sufficiently flexible to capture the conditional mean and the conditional variance of the underlying data generating process, then you're right. That's a problem.
Yes.
Yeah. Okay, so we have a filter. Now I have one slide that shows how this procedure can be applied to get parameter estimates, also a statistic for specification analysis. So here, because the auxiliary model is a linear model, we can estimate it using OS to get the regression coefficients and the residuals from that. Now, once that is done, the values can be transported using the filter that I've just described. Now I can use these components to build this updated function that measures the distance between the transported value and the actual observation. And the parameter estimate is chosen such that this quadratic form is minimized. And that defines our optimal transport estimator in the current setting. Here, because we have closed form expressions, the minimization problem is relatively easy to carry out, even for relatively high dimensional models. In terms of asymptotics, we show that we have consistency, we have square root convergence, we have normally distributed estimates asymptotically. That holds even under misspecification. Following the similar argument, we can use the magnitude of this updated function for specification analysis. Now this updated function is evaluated at theta tilde, contrasted with the actual observation, in which a significant deviation between the transported value and actual value implies that the model is misspecified. The asymptotic distribution of this statistic is not standard, but we show that it can be approximated by a weighted sum of chi-square 1 random variables, and it's easy. I wouldn't say it's easy, but it's feasible to get this approximation. So we have kind of a relatively complete package, which does filtering, parameter estimation, and it also contains a statistic for specification analysis. With that, I will turn to two empirical applications that we have. This application is for alpha term structure model. The model is taken from Hamilton Wu 2012. The model has three factors denoted by FT. This is a vector autoregression of order 1. The model imposes restrictions on the interest rates. As a result, the yield of Ampere bound can be expressed as a linear function of the factors where the parameters AM and BM satisfy certain expressions. In this representation, C and Q correspond to parameter values under the physical measure, and CQ, rho Q denote parameters under the risk neutral measure. The estimation of the model will allow us to recover parameters under both measures because they are connected to each other. The estimation is going to be based on 6 time series. So here we have 3 factors, 6 time series. As a result, the model is stochastically singular. A consequence of that is we cannot do maximal likelihood estimation. But our current procedure can easily handle this type of a model singularity. For the auxiliary model, we use vector regression of order 4. We also experimented with the same model with 6 legs. The results are quite similar. So there is some robustness in this estimation. I will only show you guys one figure from this empirical exercise. Here I have 6 time series. So the first is 1 month yield, then it's 1 year, 2 years, 3 years, 4 years, and 5 years. Those time series look quite similar, but I promise you there's no mistake. They are different time series. If you look at solid black curve, these are actual observations. If you look at the purple lines, these are model implied values. In other words, those are those YTs. And if you regress the actual observations on the model implied values, you get 97% R squared throughout. What this means, I guess, is that in this case, 3 factors can capture 97% of the variation in the time series data set. So this is without adding any measurement error to the model. In other words, we don't need additional flexibility in order to capture this 97% variation. It also means that if someone wants to generalize the model, the additional mileage is going to be between 97% and 100%. Because right now the model is already picking out 97% of the variation. So that's for this application. Now I will turn to application about the media scale DSG model. In this case, it's the Smith-Waters model estimated in 2007. This model contains 36 structural parameters and is estimated on 7 variables. Here we use the same variables, but the estimation procedure is different because we'll do the optimal transport and we use the procedure, the estimation procedure corresponding with that. And the auxiliary model is still without regression with 4 legs. Again, we experimented with 6 legs. The results are quite similar. The parameter estimates are included in the paper. Here, I will only show you guys the filtered structural shocks coming out of the Kalman filter and coming out of the OT filter that we propose. Here is the figure. The model has 7 shocks. So we have 7 plots. If you look at the black curve, that corresponds to the Kalman filter. If you look at the purple curve, the purple line, that corresponds to the OT filter. Sometimes those filter values are close to each other, but sometimes they can be quite different. In particular, if you look at the second plot, which corresponds to a Garman's bending shock, we see that Kalman filter produces filter values that are mostly negative with a downward trend. This doesn't make sense, right? Because Garman's bending shock is not supposed to be trending downward. It's just really hard to interpret. And the OT filter does not have this problem, right? It's easier to interpret in that dimension. And also, if you look at the monetary policy shock, the Kalman filter produces wild oscillations near 1980. Again, that's kind of hard to interpret because that period is supposed to be associated with monetary policy tightening, not violate oscillations in monetary policy shocks. So that's again hard to interpret. At the same time, if you look at OT filtered values, these values do tend to be positive around 1980, which is consistent with the interpretation of monetary policy tightening during that time period. Finally, if you look at the investment shock near the 1980 period, we see mostly positive values. And that's kind of hard to interpret because we don't expect to see that this period to be associated with a blessing in terms of investment technology innovations. And again, the OT filter does not have this problem. Anyway, this is just a quick illustration for the point that model consistency is quite important if you want to extract latency variables and give them some economic interpretations. That's the main part of my talk. Let me conclude. So we provide filtering and estimation procedures that take into account model misspecification, and the filter values of the states are model consistent by construction. In addition to that, a comparison between the actual observation and the filtered value of YT can potentially reveal model misspecification. And for linear processes, we have simple and fast algorithms. We also have theory for inference and testing. For comments, please email me, and this is my email address. And thank you for your comments and your attention during this talk. We expect to put the paper online, if not today, then the next couple of days. And I do look forward to your comments. Thank you.